All right, if I give you f of x is equal to 1 over x squared plus 1, I'd like you to find f prime of 2 using the limit definition of the derivative. F prime of a is the limit as h approaches 0 of the difference quotient, f of a plus h minus f of a all over h. So here we go. So in this case, the a is equal to 2. So we're going to do f prime of 2 is equal to the limit as h approaches 0 of f of 2 plus h. So I'm going to plug 2 plus h into my function wherever I see x. So it's going to be 1 over the quantity 2 plus h squared plus 1. That's my f of a plus h part. And then minus f of 2, which is going to be 1 over 2 squared plus 1. And all of that is over h. Okay, so let's simplify. And then hopefully, right now we cannot take the limit because if I just plug in 0 for h, I'll get it divided by 0. So I have 1 over 2 plus h quantity squared. And then the plus 1 minus 1 will cancel, and then minus 1/4 all over h. So we have a complex fraction, so we can combine our fractions in the numerator by getting a common denominator. And that would mean multiplying the first fraction by 4 over 4 and the second one by 2 plus h squared over 2 plus h squared. Notice I haven't squared the quantity 2 plus h yet. Try and keep things as compact and organized as I can. Limit as h approaches 0. All right, so now I can combine those two fractions and I'm going to get 4 minus, and now 1 times the quantity 2 plus h quantity squared. Let me put that in parentheses. It's going to be 4 plus 4h plus h squared. And all of that is over the common denominator of 4 times 2 plus h quantity squared. And then dividing everything by h is the same as multiplying the numerator by 1 over h. All right. And now when we simplify a little bit more, we're going to get the limit as h approaches 0. The 4's in the numerator will cancel, and I'll have a negative 4h minus h squared after I distributed that negative. And then the denominator, I'm going to have 4h 2 plus h quantity squared. And then I can factor an h out of the numerator and cancel with the factored h in the denominator. And so finally, I'll have the limit as h approaches 0 of negative 4 plus h over 4 times the quantity 2 plus h quantity squared. Now I can actually take the limit. I can plug in 0 for the h's, and I'm going to get negative 4 over 4 times 2 plus 0, which is 2, and then squared is 4. And so we get negative 4 over 16, or negative 1/4. Now, just to show with technology to make sure we know how to do that, move my calculator over here. Slide it down a little. Let's use this calculator. All right, if I punch in my original function, which was 1 over x squared plus 1, there's my graph, and I'm trying to find the derivative at 2. So if I hit trace, punch in 2, I want the derivative at that spot, or the slope of the tangent line drawn to that point. And our answer was negative 1/4, and if you can visualize drawing a tangent line at that point, negative 1/4 seems like the slope of the tangent line. So I go to second, trace, to get to the calculate menu, and I'm going to choose number 6, dy dx, which is just another notation for the derivative of y with respect to x. And I want to do it at x equals 2. Press enter. And we get dy dx is negative 0.250001. And so due to its methods of calculation, the calculator has a slight rounding error. So we're pretty safe in assuming that we have the correct answer. We're a little better than the calculator. All right. So differential calculus, derivatives. First, we need to talk about the average rate of change, or just rates of change in general. The average rate of change over an interval is the slope of the segment or the secant joining the endpoints of the interval. So for example, if I'm talking about a graph, and let's say it looks something like this, and I want to know the average rate of change from A to B, then this would be f of A and this would be f of B, if the name of our function was f, of course. And so the average rate of change over the interval AB is going to be the difference of the y's over the difference of the x's, or the slope of the secant line. So it's going to be f of B minus f of A over B minus A. And so that's important and it's useful in a lot of different applications. On the other hand, the instantaneous rate of change at a point is the slope of the tangent line at that point. So now instead of finding the slope between 2 points, we're finding the slope of a tangent line at a single point. And that's where we use the idea of taking that second point and moving it. Where's my second point? That's not it. Doesn't want to move. There it is. Taking that second point and moving it closer and closer and closer to the first point. And so then that average rate of change is getting closer and closer and closer to the instantaneous rate of change, and hence our limit definition of a derivative. So if we're given the graph of a function f of x, the gradient or slope of the tangent to the graph at x equal a is called the derivative of the function f at x equal a, and we denote it as f prime of a. And you've already seen that sometimes we'll use dy dx to talk about f prime. And the way we calculate that is by taking the limit as h approaches 0 of f of a plus h minus f of a all over h. Using this limit definition to calculate the derivative is called differentiating from first principles. Now we're familiar with derivatives already, and we spent time working through and figuring out some of the rules, the product rule, the power rule, the quotient rule. We're going to go back and revisit those. But for now, if I ask you to calculate a derivative from first principles, you have to use that limit definition. No shortcuts allowed. Now that's the derivative at a specific point. If we look at all the derivative values of a function, those themselves, along with the corresponding x values, makes another function called the general derivative function f prime of x. And it's a similar calculation, but instead of f of a plus h minus f of a in the numerator of our difference quotient, we're going to use f of x plus h minus f of x. So instead of a specific number, we're going to use the variable x, so our answer is going to be in terms of x most of the time, unless the derivative is a constant. So using first principles, find f prime of x for the function the square root of x. You might want to hit pause, calculate this, and then check your answer, or at least just for practice. All right, so the general derivative f prime of x is going to be the limit as h approaches 0 of f of x plus h, which would be the square root of x plus h, minus f of x, which is the square root of x, all over h. All right, so what do we do with this? Well, we're going to need to do some sort of algebraic manipulation because we can't take the limit as it is, because we're going to divide by 0. And so one of the techniques or tricks is multiplying by a form of 1 using the conjugate. So we're going to multiply by the square root of x plus h plus the square root of x over itself. We're allowed to multiply by forms of 1. We're not changing our expression that way, just the way it looks. So now we get the limit as h approaches 0. And if I multiply out the numerators, I'm going to get the difference of 2 squares, which is going to, in effect, cancel the square roots. So I'm going to get x plus h minus x. Now in the denominator, I'm going to leave this factored. I'm not going to multiply it out. Because that's the whole idea, is we try and factor out an h so we can cancel with the h in the denominator, and then we can apply the limit. Now the x's cancel out. X minus x is 0, and then we have an h on top, which reduces with the h on the bottom to 1. And so now I can take the limit, and as h goes to 0, I'm going to get 1 over the square root of x plus 0 plus the square root of x, which is 1 over 2 root x. And that's the general derivative for f of x equals the square root of x. Or if you want to write that as 1/2 x to the negative 1/2 power. That would work as well. All right, so differentiating from first principles to find a specific derivative at a point or the general derivative. Now let's talk about differentiability. That means, does a function have a derivative at a point? So if a function is differentiable at a point x equal a, then it has to be continuous at x equal a. But the inverse of that statement is not necessarily true. Just because a function is continuous at a point does not mean that it's differentiable at that point. And that's really, really important to remember. So if you're looking at a function and you want to find the derivative at a point, if it's not continuous there, then you don't even have to bother. It's not differentiable there. But even though if it is continuous at that point, it still may not be differentiable. We'll do an example in a minute. As a review of what it means to be continuous at a point, if a function is continuous at f of a, then all three of these following things have to be true. And I'll give you a little counterexample. First of all, f of a has to exist. So something that would violate that. Here's a. Let's say we had a function there. F of a does not exist. So the function's not continuous at a. What else has to be true? The limit as x approaches a of f of x has to exist. The limit has to exist. So let me draw an example where the first one will hold, but the second one does not. So let's say, for example, we have, we'll put a closed circle here and an open circle, straight line. All right, so for this example, f of a does, put a on here, f of a does exist, but the limit as x approaches a does not exist because the left-hand limit and the right-hand limit are not equal. The third thing that has to be true for a function to be continuous is the limit as x approaches a of f of x has to equal f of a. Counterexample to that. Let's say, for example, we had, how about something like this? There's our function f. Here's a. And we go through number one. Does f of a exist? Yeah, sure. Does the limit as x approaches a of f of x exist? Yes, it does. But does that limit equal the value of the function? No, it does not. So all three of these have to be true. So these would be all counterexamples. All three of those statements have to be true for the function to be continuous. And if it's not continuous, then it certainly is not differentiable. All right, so differentiability. A function is differentiable at x equal a if f is continuous at x equal a. So that's the first standard that has to be met. And then secondly, now that's a lot to look at, so let's focus at one thing at a time here. Draw an arrow. So this means the derivative, the left-hand derivative, and this means the right-hand derivative, from the right plus, from the left minus. So if we take the limit of the difference quotient as h approaches 0 from the left, so that means h has negative values getting closer to 0. And then this one is the limit as h approaches 0 from the right of the difference quotient. And that means that h is greater than 0 but getting smaller and smaller and smaller. So basically, from both sides, that limit has to exist and has to be equal. So let me give you one last example. Discuss the differentiability, easy for me to say, of the absolute value of x. So let's take a look at that picture. What does the absolute value of x look like? Well, we've seen this many times before. There's our absolute value of x. Like that hit right there. Perfect. All right. So let's say I'm trying to find the derivative at 0. If h is a positive number, it's over here, then I'm looking at the slope. And as h gets smaller and smaller, this is getting closer and closer to 0. What's the slope? Well, the slope is a constant 1. So the limit as h approaches 0 from the right is 1. But what happens when I'm on the other side, when h is negative? Now when I'm calculating the slopes, I'm getting negative 1, negative 1, negative 1, negative 1, negative 1. So the left-hand limit is negative 1. So the left-hand limit and the right-hand limit of the difference quotient are not the same. So that tells me that f prime of 0 does not exist. Everywhere else on that graph, the function is differentiable. Because wherever you want to put your point, coming in from the right or from the left, we're approaching the same value for our slope between these 2 points. Doesn't matter where we're at, from the left, from the right. Okay? But at this point, no good. Now, how's that different from, let's say, a parabola? Well, if I have a parabola, y equal x squared, and I want to look at, well, how about the derivative at 0 for that? Well, what happens here? When I'm calculating the slope, that's steep, but then it's not a constant. It's not a constant value. It's getting less steep and less steep and less steep and closer to 0 as this gets closer and closer. So the limit of the slope between these 2 points, as the green point gets closer and closer to the red point, is 0. Over on this side, the slope is negative, pretty steep, still negative but less steep, still negative but even less steep, still negative but closer and closer to 0 from the left. So the limit of that difference quotient from the right is approaching 0, and the limit of the difference quotient from the left is also approaching 0. So that's why the derivative at x equals 0 for the parabola does exist. So basically you can't have any sharp corners or cusps where your graph comes to a sharp point. Then it's not differentiable there. All right, so some problems at the review of chapter 16 starts on page 432.